Hello there, Mr. Sutton here, bringing you the BC Calculus 617 Extra Practice Number 1 solutions on Euler's method. For this problem, we're given a table with values of f prime, and we're told if f of 1 equals 4, we want an approximation for f of 2 using Euler's method with a step size of 0.5. So they've laid it all out for us. We're starting at x equals 1, and we need to take 2 steps, each of them 0.5, to get to x equals 2. We're going to start by figuring out what f of 1.5 is. And then once we have that, we'll use that to figure out f of 2. So f of 1.5, that's going to be f of 1 plus f prime of 1 times our step size of 0.5. F of 1 they told us was 4. F prime of 1, we're actually given that in the table, that's 0.2. And then our step size of 0.5 gets multiplied by that. So we've got 4 plus, this will be 0.1. Which ends up being 4.1. Now that we have f of 1.5, we're going to use that to figure out f of 2. So f of 2 is going to be f of 1.5, which we just approximated there, plus f prime of 1.5 times our step size of 0.5. F of 1.5 we got was 4.1, or at least that's the value we're going to use with Euler's method. And then f prime of 1.5 in the table is 0.5. So that gets multiplied by our step size of 0.5. So we've got 4.1 plus essentially 0.25. That's 4.35, which ends up being answer choice C. On this problem, we're given the differential equation xy over 2. And let's see, f of x is the particular solution, initial condition f of 0 equals 3. We're using Euler's method, starting at x equals 0, step size of 0.1, to approximate f of 0.2. So we're going to do this in 2 steps. First, we're going to figure out f of 0.1. Then once we have that, we can move to finding f of 0.2. To get f of 0.1, we start with f of 0, and to that we're going to add f prime of 0 times our step size of 0.1. F of 0, they said, was 3. F prime of 0, that's what I get when I plug the x value 0 and the y value that goes with it, 3. Into this differential equation. So that's 0 times 3 over 2, which just comes out to 0. So we've got 0 times 0.1. So this all comes out to 3. That's our approximation for f of 0.1. Now we're going to use that to get f of 0.2. That's going to be f of 0.1, which we just found up here, plus f prime of 0.1 times our step size of 0.1. F of 0.1 is 3, approximated. F prime of 0.1, that's going to be 0.1 times the y value that we approximated of 3, all that over 2. So this is 0.3 over 2, which is 0.15. So we've got 0.15 times 0.1 over there. And let's see, that's really, if we move the decimal 1 more to the left here, that's 0.015. So then 3.015 ends up being our final answer. For this calculator-based free response problem, f is a function whose graph goes through 3, 6, and its derivative is given by this f prime function. First part of this problem, they want an equation of the line tangent to the graph at x equals 3, and then they want us to use that to approximate f of 3.1. So I'm going to use my tangent line formula here. L of x equals f of a plus f prime of a times x minus a, which doesn't get me any credit on the AP, but at least tells me what I need to figure out. So f prime of 3 is going to be, let's see here, they told us that, it's going to be 6. At the x value 3, we have a y value of 6. So f of 3, then we've got 6, plus f prime of 3. Well, that's what I get when I plug 3 into this formula here. So that's going to be 1 plus e to the third over 3 squared, or 1 plus e to the third over 9, which I'll put over here now. And then we're multiplying that by x minus 3. Okay, so we've got our tangent line equation. That's sufficient for answering that part of the question. Now we need to use this to approximate f of 3.1. So the very first thing I'm going to write is f of 3.1 is approximately equal to 6 plus 1 plus e to the third over 9 times 3.1 minus 3. Now this is numerically equivalent to whatever answer they're looking for, so you could actually leave it like this for full credit. However, if you wanted to do this on the calculator to get the decimal, let's do that now. Just plugging all that in exactly as it's written. I get about 6.234 if we take it out to 3 decimals of accuracy. On this problem, they want us to use Euler's method from 3 to 3.1 with a step size of 0.05 to approximate f of 3.1. And then they have some other stuff they want us to do after. Let's start with Euler's method, though. So to get to f of 3.1, I have to start by doing f of 3, or actually 3.05. But for that, I'm going to need f of 3 plus f prime of 3 times our step size of 0.05. So f of 3, they actually gave us, that's going to be 6. And then f prime of 3, I'm going to have to plug 3 in here. So I've got 1 plus e to the third over 9 times 0.05 then. And let me just get a decimal value now. This is a calculator problem. So plug in all that in. We get about 6.1171. I'm going to take it out to 4 decimals here for accuracy. And now we're going to use that to approximate f of 3.1, which is going to be f of 3.05 plus f prime of 3.05 times our step size of 0.05. So we've got 6.1171 for f of 3.05. That's our approximated value. Then f prime of 3.05, well, that's just going to be 1 plus e to the 3.05 over 3.05 squared. And we're multiplying that again by our step size of 0.05. So let's plug this into the calculator now. So this was a bit of a mess to plug in, but here it is. There's my decimal in the beginning, that crazy fraction, and the 0.05 at the very end. And this is all coming out to about 6.2360 if we round off to 4 decimals, really 3 decimals if you come down to it. All right, so that was our first step. We got our Euler approximation. Now they want us to use f double prime to explain why this approximation is less than f of 3.1. So just like with tangent line approximations, with Euler, which is basically tangent line approximations over and over again, we have to look at the concavity between the launching off value, which in this case was 3, and the final value, which is 3.1, to see what the concavity is on that whole interval. And if it's concave up on that whole interval, then we know that we under-approximated. Concave down on the whole interval, then we over-approximated. Now they want us to use f double prime to figure this out. There's a few ways you can do this. You can actually figure out f double prime and get the algebraic version of f double prime of this. Set it equal to 0 on your calculator and see where it's positive versus negative. And that's a fair amount of work. Another way to do this, kind of a sneakier way, is just to graph out f prime and see whether it's increasing or decreasing. That will tell you directly whether f double prime is positive or negative. So that's what I ended up doing. I'm going to do that on the calculator with us now. So here's my f prime in my y equals, and I'm just going to go to a window of 3 to 3.1 because that's really the only interval I need to figure this out for. And then I'll do a zoom fit for this. And if I do that from 3 to 3.1, I see that f prime is increasing the whole time. So there's my graph. I can write out, because this is just a direct observation from my graph, that f of x is, or f prime of x is increasing on 3 to 3.1. Now, this would be enough to tell us whether the original function was concave up or down, which would give us what we needed for the approximation over or under piece of it, but they specifically said to use f double prime. So if you want to use this approach to get f double prime, you next have to say this means f double prime is positive on the interval from 3 to 3.1. And you can then use that to conclude whether we're over or under. If f double prime is positive, that means f is concave up, which means that our approximation here, 6.2360, is going to under-approximate the true value of 3.1, f of 3.1. On this problem, they want us to use the integral from 3 to 3.1 of f prime of f of x dx to evaluate f of 3.1. So this is just using fundamental theorem. We can say that f of 3.1 equals f of 3, and we're saying f of 3 because we know what f of 3 is, it's 6, plus this integral right here. And now we just have to do that on the calculator. And specifically on the calculator, I'm going to be entering 6 plus that integral. So before I do anything else, if I hadn't already on that previous part, I'm going to enter this f prime as y1 just to make it a little easier to deal with. And now on my main screen, I've got that 6 there plus math 9, the integral from 3 to 3.1 of, and now I'm going to do alpha trace to get my function menu. We've got y1 we're putting in there. We'll do dx, enter, and that's about 6.238 if we round it off. On this problem, we have f as a function that satisfies f prime of x equals negative 3x f of x, and we're given a value of f here and also a limit value, which is kind of nice. First part of this, they want us to evaluate the integral from 1 to infinity of negative 3x f of x dx, showing our work. Very first thing you have to do on this, since it's an improper integral with this infinite limit of integration, we have to turn this into a limit. So I'm going to rewrite this as the limit as b approaches infinity of the integral from 1 to b of all that stuff that's inside. Okay, so now we can actually use our normal integration process here. Before we can do that, though, there's one problem. We know nothing about the f function in terms of finding its antiderivative. But what we do know the antiderivative of is f prime. We know the antiderivative of f prime, by definition, is f. And we also have an equation up here with an f prime and an f in it. So we're going to rearrange this equation to rewrite this f of x here in terms of f prime. That'll make our integration easier on the next step. So right here, to get f of x by itself, I'm just going to divide both sides by negative 3x. So I can write f of x equals f prime of x over negative 3x. Substituting that back in over here, we've got the integral with all that limit infinity stuff of negative 3x times f prime of x over negative 3x. Now this is a really nice substitution because you notice these negative 3x's also just so happen to cancel out completely, which makes our job way easier for the next step. At this point, we can now take the antiderivative of f prime, which is just f. So we want the limit as b approaches infinity of f of x evaluated from 1 to b. So this is limit as b approaches infinity of f of b minus f of 1. Now we actually have to find some numbers here. So limit as b approaches infinity of f of b, that's what this statement up here is, essentially, except with x's instead of b's. We see that as the input approaches infinity, the f function approaches 0. So this f of b here becomes 0. And then f of 1, they told us, is just 4. So this evaluates to 0 minus 4, and now we can get rid of our limit notation now that we've actually, quote-unquote, plugged things in. So we can simplify this then to negative 4. For this problem, using Euler's method and starting at x equals 1 with a step size of 0.5, we want to approximate f of 2. So we're going to do this in 2 steps. First, we're going to figure out f of 1.5, and then we'll use that to figure out f of 2. So f of 1.5 is going to be f of 1, approximately f of 1, plus f prime of 1 times our step size of 0.5 that they gave us. F of 1, we know from what they told us here, is 4. F prime of 1, well, now we have to plug 1 into f prime up here. So that's negative 3 times 1 times f of 1. So what's f of 1 again? Oh yeah, it's 4. So this is really just negative 3 times 1 times 4, or negative 12. So this is going to be negative 12 times 0.5. This is essentially 4 minus 6, which is negative 2. Okay, now we're going to find f of 2. That's going to be f of 1.5, which we just approximated, plus f prime of 1.5 times 0.5 step. F of 1.5, well, we already said that was approximately negative 2. F prime of 1.5, now we're doing negative 3 times 1.5 times f of 1.5. So this is going to be, let's see, negative 4.5 times whatever f of 1.5 is. Well, we approximated that f of 1.5 was negative 2. So we're basically doing negative 4.5 times negative 2. And this is an approximation, so we're going to write approximately equals positive 9 for all that. So we've got positive 9 here times 0.5. We've essentially got negative 2 plus 4.5, which is 2.5. For For this problem part, they want an expression for y equals f of x by solving this differential equation, dy over dx equals negative 3xy. Initial condition of f of 1 equals 4. So pretty much what they set up here, only they substituted out an f of x for a y. All right, so first step here, we notice that we have an output variable, y, in our differential equation. That means we need to use separation of variables. So I'm going to divide both sides by y to get 1 over y times dy on the left side. And then I'll multiply dx to be on the other side, so I'll have a negative 3x dx over there. Now I take the antiderivative of each side. On the left side, we've got ln absolute value of y. On the right side, this bumps up to a 2 for the exponent. Dividing by that, we've got negative 3 halves x squared plus c. Now I'm going to use my initial condition, 1 comma 4, to figure out what my c value is. So on the left side, I've got ln absolute value of 4. And I don't really need the absolute value at that point, but I'll leave it there. And then on the right side, we have negative 3 halves times 1 squared plus c. So this is going to be just negative 3 halves plus c on the right side. If I add that over on the left side, I've got ln of 4 plus 3 halves. And that's my c value. It's not pretty, but it's a constant, so we're going to move on to the next part of the problem, which is to substitute this back in to our general solution up here. Before we do that, though, we need to figure out what's going on with this absolute value. Is the stuff inside going to be positive or negative? They gave us an initial condition where y equaled 4. So if y equals 4, that means the stuff inside my absolute value is positive. So I can rewrite this as just ln of y with either a parentheses or just nothing at all. So that's going to equal negative 3 halves x squared. And then we're going to have our c value being added on there, plus ln of 4 plus 3 halves. One more step, we just have to isolate y. We can do that by raising e to both sides. So we can write y equals e to the everything on the right side of the equation there. And if you wanted to be really fancy, this ln of 4 can come out as a 4 in front of the e, and that's another way of writing this expression. For this problem, we've got this crazy-looking differential equation, and f is the particular solution to this with an initial condition of negative 1 comma negative 4. We want to use Euler's method from x equals negative 1 to 0 to figure out f of 0, and they want 2 steps of equal size. So that means that we're going to have to use steps of 0.5 to get from negative 1 to 0 in 2 steps. So we're going to start by figuring out f of negative 0.5. That's the first step to get from negative 1 to 0. So that's going to be f of negative 1 plus f prime of negative 1 times our step size that we just figured out of 0.5. Now f of negative 1 they told us was exactly negative 4. F prime of negative 1, I've got to plug negative 1 and the y value that goes with it, negative 4, into my differential equation. So this is going to be 5 times negative 1 squared minus 6 over negative 4 minus 2. This is going to be 5, and then this all comes out to positive 1 when the dust settles. So 5 plus 1 comes out to 6. So we've got negative 4 plus 6 times 0.5. So that's going to be negative 4 plus 3, which is negative 1. Next up, we need to find f of 0. So that's going to be f of negative 0.5, which we just found up there, plus f prime of negative 0.5 times a step of 0.5. F of negative 0.5 we approximated as negative 1. Now for f prime of negative 0.5, I've got an x value of negative 0.5, so 5 times negative 0.5 squared, minus 6 over, and now for the y value, we're going to use this negative 1 that we approximated. So 6 over negative 1 minus 2. So let's see here. We've got, this is 0.25 times 5. So that's going to be, let's see, 1.25. And then over here, we've got 6 over negative 3, which is negative 2, but we're adding that. So this was then 1.25 plus 2, which is 3.25. So we have 3.25 times 0.5 over here. Next, and by the way, this was a no calculator question, as crazy as it sounds. So you could actually leave it like this, and that's numerically equivalent to the right answer. Or if you wanted, you could go a step further. So what's half of 3.25? So this is one you would probably do out by hand, dividing 3.25 by 2. That does come out to 1.625, which if you add that to the negative 1 here is going to be just positive 0.625. For this problem, we're given this differential equation and this slope field. We don't really need the differential equation for part A that we're doing here. They just want us to sketch solution curves through 3, 2 and 0, 8. So for 3, 2, which is right here, we need a curve that follows the tangent lines, goes through that, and follows the other tangent lines. So something that goes like this if we're following the tangent lines. We do have a horizontal asymptote up here that we have to follow. And now for 0, 8, we're just going to come down like this and also approach that horizontal asymptote. For this problem, we're given this differential equation, and we want to figure out, using Euler's method, what f of 1 is. We're starting at t equals 0, and we're given that f of 0 is 8. So to go from 0 to 1 with 2 steps of equal size, we need to go by 0.5s. I'll start by figuring out f of 1/2, or f of 0.5, either way. So that's going to be f of 0 plus f prime of 0 times a step size of 1/2. F of 0, they told us, was 8. F prime of 0, well, I'm plugging x into my differential equation, but there is no place to plug in x. There's a place to plug in y. So I actually have to plug in the y value that goes with the x value of 0. So 8. We'll have 8 over 8 times 6 minus 8. This is just 1 times negative 2, or negative 2. So this is 8 minus 2 times 1/2. 8 minus 1 is 7. So that's our approximated value of f of 1/2. Now we're going to use that to find f of 1. F of 1 is going to be approximately f of 1/2 plus f prime of 1/2 times a step size of 1/2. F of 1/2 we said was 7 approximately. F prime of 1/2, now we're plugging in the y value that goes with x equals 1/2, namely 7, into this. So we have 7 over 8 times 6 minus 7. That's 7/8 times negative 1, or negative 7/8. So this is negative 7/8 times 1/2. And you could actually leave it like this and call it a day. Or you could try simplifying it. This is going to be 7 minus 7/16. Well, how many... So what's that going to end up being? Well, that's going to be 6 and 9/16, or 105 over 16 if you do all the fraction math on that one.